Hello, Professor. We could start.
Okay, let's start. Recall that our aim is to construct a simple spherical variety from a colored cone. So given a colored cone, C comma B, C is a strictly pointed cone in the vector space E, and B is a subset of colors. Given a colored cone, we want to construct a simple spherical variety with a unique closed orbit Y, such that the colored cone of this X is exactly the cone we started with. And the construction we suggested at the previous lecture is the following one. So let me recall some notation. We denote the complement of the set of colors B, the divisors, the colors in this complement, we denote it by D1, dt. V1, VR are the generators of the extremal rays of the cone C, those rays which do not contain a vector corresponding to a color from B. Okay? And also lambda 1, lambda n are the generators of the semigroup of lattice vectors in the dual cone, C check. So here is the picture. You can see on the picture how all these things look like. So you see the generators of the cone CY, those corresponding to colors denoted by D of different color, and those corresponding to G-stable prime divisors, this V1, etc., VR, this VIs in green. And also you see the colors not contained in B marked by black. There's a single color of such kind on the picture, but there may be more, of course. And the dual cone, which formally sits in the dual vector space, but I put it on the same picture. The dual cone is marked by yellow, and the generators of the lattice semigroup of lattice vectors in this dual cone are marked by yellow arrows. So some of these generators belong to the extremal rays of the dual cone, but there may be other generators which do not belong to extremal rays. So we take all generators. Okay, now we consider the divisor, the effective divisor on our spherical homogeneous space Y0, which is just the sum of all colors not contained in B, with some sufficiently big multiple, taken with sufficiently big multiple, so that the respective line bundle L is equipped with an action of G. So the action of G is lifted from the open orbit, from the orbit Y0 to this line bundle L. And this divisor delta defines a canonical B semi-invariant section of the line bundle L, denoted by S0. Such that if you multiply this S0 with rational functions, with rational B semi-invariant functions corresponding to generators of this lattice semigroup, then you obtain sections with no poles. You obtain regular sections. For this purpose, M is taken sufficiently big. And so we get also B semi-invariant regular sections of the same line bundle L, denoted by Sj. Next, we generate a simple G submodule in the space of sections by each of these Sj's. These Sj's are just highest weight vectors in this submodulus Mj. And we take the sum of all these simple submodules. This M is a G submodule, a finite dimensional G submodule in the space of sections of L. And this finite dimensional space of sections defines a map, a G equivariant map from the homogeneous space Y0 to the projectivization of the dual space M star. Now we denote by X bar the closure of the image of this map, the closure of the image of the homogeneous space Y0 under this map. By X by X upper node, we denote an affine open subvariety in X bar obtained by removing this hyperplane section. And finally, by X, we denote the G-span of this affine B-stable open subset X upper knot. So this X will be our X. We shall prove that this X will be indeed the simple spherical variety such that its colored cone coincides with the initial one, with this one. So what we already did in the course of the proof, we proved that we obtained a description of the coordinate algebra of this affine B-stable open subset X upper knot. Formally, this coordinate algebra is generated by rational functions in the set M divided by S naught. So when you remove the hyperplane section, you obtain the affine chart, and the affine coordinates on this affine chart are just projective coordinates, that is basis elements of M divided by S naught. So this space M divided by S naught generates the coordinate algebra of X naught. But we obtained another description of this coordinate algebra. This coordinate algebra is canonically embedded in the space of rational functions on the orbit y lower knot, on this guy. And it consists exactly of all functions which are regular on the open B orbit, y upper knot. This means that F has a B-stable divisor of poles. And yet other conditions are that the evaluations corresponding to the generating vectors of the cone C, the evaluations corresponding to these vectors V1, Vr, and the vectors Vd bar, where D ranges over B. So all these valuations take non-negative values on F. So this is the description of the coordinate algebra of X upper knot, which we obtained. And from this description, we deduced that X upper knot, and therefore its G-span, X, G-span of X upper knot, these are normal varieties, normal algebraic varieties. This is what we have proved at the previous lecture. Yes.
Did we prove that the map from Y naught to the projective space is injective or something?
Not yet, not yet. We didn't yet prove that this map is injective, and this is our next aim. So our next step, the next step of the proof, is to prove indeed. So we proceed with the proof. We proceed with the proof. And our next step will be to prove that the map phi is injective, that the map phi gives an open embedding of Y naught into X. So the map phi identifies Y naught with the open G orbit in X. Okay. Well, actually, it suffices to prove that this map is birational. And for this purpose, because since it is birational, it is injective on some open subset. But since it is G equivariant, it is injective on the whole orbit Y naught. Then, for this purpose, it suffices to prove that the field of rational functions, on X, or which is the same thing on X upper knot, contains the algebra of regular functions on the orbit Y upper knot. Well, formally speaking, maybe I should be more precise. So this field of rational functions, or in other words, the field of rational functions on X, is embedded into the field of rational functions on y0 by the pullback map of phi. Yeah. So we can identify this field with the subfield of this field. Okay. And this algebra is also the subfield of the same field.
So did we prove that x upper node is open in X?
It is obvious because, well, it is just from the construction, because X upper node is open in X bar.
Upper node yes, it is open in X bar, and X is a sus.
X is a G span, so X is a union of G shifts of X naught, so it is contained in X bar. X is also open in X bar, and X naught is contained in X. So X naught is open in X. Okay. Maybe yes. Let me again draw a picture. So the picture is like this. So you have X bar. You have X sitting in X bar. As an open subset, and you have X naught sitting in X. Something like this. So these are inclusions of open subsets. Okay, let's go on. So as I said, the pullback map of phi embeds this field into this field. But if we prove that the pullback of this field contains this subalgebra, then this field will be equal to this one. The pullback of this field will be equal to this one, because y upper node is an open subset, an open affine subset in y lower node. So the fraction field of its coordinate algebra is the same as the field of rational functions on here or on here, doesn't matter. So it suffices to prove this inclusion. Let's do it. Here we use the conditions first. For the first time, we use the conditions on the colored cone. So we know that by definition of the colored cone, that the cone C is pointed. Okay, the cone C is pointed. And the vectors VD bar corresponding to the colors in the set B are non-zero for any D in B. This is just by definition of the colored cone. And this implies that there exists a lattice vector in the dual cone. See, check. A lattice vector such that for any of the vectors v1 vr, so for any I ranging from 1 to r, we have the pairing of vi with lambda is strictly positive. And also for any D in B, the pairing of VD bar with lambda is strictly positive. Just look at the picture, at the same picture. So since this cone is pointed, it lies on one side from some hyperplane. It lies in one of the open half spaces defined by some hyperplane. There is a hyperplane intersecting this cone exactly in the vertex in 0. for instance, let me draw it here, this hyperplane, well, like this one, yeah, okay, maybe even thinner. Let it be this one, okay. And I take lambda to be just how to say, to be the linear function on the space E, defining this hyperplane. So this is the direction vector for lambda, like this. Excuse me. This will be lambda. Lambda from this formula. So such a lambda exists, okay? And this means that if you take any regular function on the open B orbit, this function may have poles only outside the open B orbit. So the poles of this function f are B stable, and in particular, so what I want to say, yeah. So I want to say that if you take an arbitrary function regular on y upper knot, then if you multiply this function f by a sufficiently big power of so if you consider f times f lambda to the power k, where k is sufficiently big, so that so you see that this semi-invariant function f lambda.
Where is f lambda chosen from?
F lambda is taken from this lambda. So lambda is a lattice vector in the weight lattice, and you may consider a semi-invariant function corresponding to this weight.
So f lambda sitting in ky.
Well, f lambda. Let me write. F lambda is sitting in the field of B semi-invariant. So in the semi-group of B semi-invariant rational functions in here.
I know.
Okay. So and the formula which you see here, this formula, mean that this function f lambda has zeros along the divisors D corresponding to colors, and also these valuations take positive value on f lambda. And this implies that if you multiply an arbitrary function f by f lambda with to a sufficiently big power, then you take this power as big enough to obtain that the value of vi on this product will be non-negative, and also the value of the valuation corresponding to the divisor D from B, to any divisor D from B, will be non-negative on this power. So you may kill negative values of VIs and VDs on F by multiplying it with sufficiently big power of F lambda, because for F lambda these values are positive. Okay, so you get non-negative values for sufficiently big K. But in view of the first step, in view of this description of the coordinate algebra of X upper knot, this means exactly that this product function belongs to this coordinate algebra. So this implies that f times f lambda to the k belongs to the coordinate algebra of x upper naught. And for the same reason, f lambda itself belongs to the coordinate algebra of x upper naught, because for f lambda, the same inequalities are satisfied, and even these inequalities are strict for f lambda, even more. So these two inclusions imply, of course, these two inclusions imply that f is contained in the fraction field of the coordinate algebra, that is in the field of rational functions of x upper naught, and we are done. So we have proved that any function from here is contained in here.
So why is f lambda belongs to because
f lambda is the ratio of these two guys. You may divide this guy.
Non-negative condition. I see it.
Okay. So we have done the third step. Are there still any questions on the third step? No questions so far. Then let's turn to the next step. So we have proved that this x we constructed here is indeed an embedding, an open embedding of my homogeneous space Y0. Now we want to prove that x is a simple embedding, that x contains a unique closed G orbit. This will be our next step. Step 4. We prove that x is simple.
This is the last step, right?
Not yet.
Oh, why?
Because we also want to prove that the colored cone of x is exactly this guy.
Oh.
Okay? But we move towards this final goal step by step. So how to prove that x is simple? Well, here yet another condition from the definition of the colored cone comes into play. Namely, the colored cone satisfies the property that the intersection of the relative interior of it with the evaluation cone is non-empty. So we may choose a vector, say v, sitting in this intersection, which sits in the relative interior of the cone C and also in the evaluation cone. Okay? Because this guy is non-empty by definition of the colored cone. So we use the conditions in the definition of the colored cone, of course. Choose such V, then I claim that so V may be considered as evaluation since it sits in the evaluation cone. This vector V corresponds to evaluation of the field of functions, which will be denoted by the same letter, of course. And I claim that this valuation is greater or equal than 0 on this space of functions, M divided by S naught. So recall that, again, let me come back to the first page. Recall that M is a G submodule in the space of global sections spanned by all these SJs. And SJs are obtained from S naught by multiplying with F lambda Js, where F lambda Js are the generators of this semigroup of lattice vectors in C check. So clearly, since V, maybe I should draw yet another. So my picture becomes more and more rich. Let me draw yet another ingredient. So, excuse me. Let me make it smaller. For instance, let this guy will be my V. Okay, this V sitting in the interior of the cone C and in the evaluation cone at the same time. So this guy will be my V. and since V sits in this interior, then in particular, it takes positive values on all these lambda j's. Yeah, so the pairing of V with all the lambda j's is positive. And this means that V takes positive values on all these functions f lambda j's. And therefore, it takes positive values on the ratios Sj over S0. In other words, if we extend V, we can extend a G invariant valuation to a bigger field. If we extend V to the fraction field of the algebra of sections of all powers of L, as we did before, then the value of V at Sj is greater than the value at S0. And the same holds for any vector in the G module spanned by Sj, because the value of a G invariant valuation on a simple G module is constant, as we know. And also by the additive property of the valuation, that the valuation of a sum is greater or equal than the minimum of the valuation on the summons, we get this. We get this inequality. So in fact, the argument is exactly, yeah.
So I mean, we know that the value of V at Sj is positive, right?
No, we don't know that the value of V on Sj is positive, because so far
the value of it on f lambda j is positive. Oh, so it is positive.
We know that the value on here is positive. We know that the value on here is positive, and the value on Sj therefore is greater than the value on S0, because it is the sum of the value on here and on here. Yeah. So the value on here is greater than the value on here because the value on here is positive. Okay.
Okay.
Let me just finish. This holds for j bigger than 0, and for j equal to 0, the value on here is of course equal to the value on S0 because it is the same thing. So in general, on the whole of M, we have an inequality which is not strict. This inequality gives rise to an equality on M0 on here. And this inequality is strict on all other summons. So this is how this inequality looks on M over S0. Okay. Okay. So, So briefly speaking, so the argument which I just reproduced is the same, exactly the same as in the proof. Let me just write that the argument is exactly the same as in the proof of the first step on the previous lecture. Sorry, another color. As in the proof of step 1. Okay. In the step 1, we proved the same inequality for the vectors Vj, for the valuations Vi corresponding to these generators. Yeah. And I guess that even you asked me a question, why not to prove the same inequality for any V in the valuation cone intersected with Cy. Now we do it. Now we finally do it. Okay. This implies. Let me continue the argument. This implies that V is greater or equal than V of S0. Oh, this is the same thing, more or less, that V is greater or equal than V of S0 on M. And this implies, in turn, that V is greater or equal than D times V of S0 on M times etc. m d times. Or in other words, this is the same as the d-th homogeneous component of degree d in the coordinate algebra of the affine cone over x bar. Yeah, so this space M is just the space of linear functions on this affine cone. Yeah, and the space M times M times M d times is the space of homogeneous forms of degree d in projective coordinates, or the same of homogeneous polynomials of degree d on the affine cone over x bar. This is the same. This is by multiplicative property of the evaluation. So this inequality implies this inequality. Okay. Now let us define an ideal in the coordinate algebra of this affine cone. So we consider the ideal denoted by script I. It is a homogeneous ideal. It is the direct sum of IDs over all D ranging from 1 to infinity. Well, this space ID, I write it here maybe, is defined as the space of all homogeneous forms of degree D, that is elements of this M times M times M D times, such that this inequality holds on F. So let me move it to the left. I have not enough space here.
We sum from 1, not from 0.
Not from 0, because formally you can define this for 0 as well. Then F will be just scalars. But for scalars, this value, both values are 0. So we have equality here. And I want to have a strict inequality. I want to have a strict inequality that is V of F is greater than D times V of S naught. So this is the definition of this guy I sub D. So this is so on the whole algebra or on the whole of the space we have an inequality which may be non-strict, and when we make this inequality strict, this identifies a G invariant G stable subspace in this guy. In this guy, or if you like the same thing in this guy, this is the same. Okay. Well, so I claim that this is a G stable prime ideal in the coordinate algebra of the affine cone. So I claim that this guy is like this, and this guy is a G stable prime ideal. An easy exercise for you is to prove it. So let me write it as an exercise. To prove this statement. Well, G invariance is more or less obvious because this condition is G invariant, since you have just a constant on the right and V is a G invariant valuation. So when you act on F by some element of G, nothing changes here. So G invariance, G stability is obvious, and it easily follows from the properties, from the defining properties of valuations, that this I is indeed an ideal, and it is a prime ideal. This means that if a product of two elements sits in Y, in I, then one of the factors must belong to I, okay? So it is a prime ideal. And since it is a prime ideal, it defines an irreducible G-stable algebraic subvariety in this affine code. Or if you like, if you consider this ring as a homogeneous coordinate ring of X bar, then this ideal in the homogeneous coordinate ring of X bar defines an irreducible G-stable subvariety, projective subvariety in X bar. But X bar is spherical, so there are finitely many G orbits in X bar. And therefore, any G-stable irreducible subvariety in X bar is just the closure of one of the orbits. So this means that this G-stable prime ideal I, script I, is just the vanishing ideal. So this I is just the vanishing ideal of some G orbit in X bar, sorry, in X bar. Okay. Also observe that this ideal I does not contain the section S0 itself. Because if you take S0 for F here, then D is equal to 1, then you have an equality here. V of S0 on the left side and on the right side, okay? So this is a proper ideal. So this is a proper ideal. It does not contain S0. And this means, in turn, this means, since J does not contain S0, this means that the orbit Y on which this ideal vanishes, this orbit Y is not contained in the complement of S0, or is not contained in the vanishing locus of S0. Since the vanishing ideal does not contain S0, the variety which it defines is not contained in the vanishing locus of S0. This means, in other words, that Y intersects X upper node, this open affine subset, bistable subset, which is the non-vanishing locus of S0. So this intersection is non-empty. So the picture is like this. Let me again come back here. So we have this orbit Y, maybe, so I have black, green, blue, let me put it in red. So we have this orbit Y in X bar, this orbit Y in X bar, yeah? And this orbit Y intersects the non-vanishing locus of the section S0, and so it intersects X. It is contained in X. Maybe I should remove this extra red lines here. Let me make this line shorter, because this is an orbit, a single G orbit, and it doesn't go outside X. It doesn't go outside X. It looks like this. It is an orbit in X. It intersects X0, and therefore it is contained in the G span of X0. Okay.
So since Y is the vanishing order of an ideal, of a prime ideal, so Y is closed, right?
No. Actually, the vanishing ideal of Y is the same as the vanishing ideal of the closure of Y, because Y is dense in its closure. So I could put the closure of Y here, if you like. The correspondence between ideals and subvarieties is between ideals and closed subvarieties, of course. So I could put the closure of y here, but it is the same. If a function or a section
so y is not necessarily closed.
Y is not necessarily closed in here. Y is not necessarily closed in here, but we shall prove that y is closed in X. This will be our next goal to prove this. Actually, we shall prove the following. We shall prove. Let me write it explicitly. We shall prove that y is contained in the closure, that y is contained in the closure of any other orbit in X. Okay? If we prove this, then in particular, this will imply that y itself is closed. In particular, y will be closed in X, not in X bar. Okay? So how to prove this? How to prove that y is contained in the closure of any other g orbit in X? We shall again use the blow-up construction. Blow-up construction. We shall blow up. This closure of y prime in X. So we have the closure of y prime. It is a closed subvariety in X. Closure in X, I mean, of course. And we can blow up this subvariety, and then we obtain yet another spherical variety X prime, containing a prime divisor, a prime G-stable divisor D prime, which maps to this closure. Well, if the exceptional divisor has several irreducible components, then as I explained on the previous lecture, we can remove all of them but one, which maps dominantly onto y prime bar. Okay, so we have this picture. Then this gives us a G-invariant valuation V prime corresponding to this divisor D prime. This is a G-invariant valuation, or if you like, a vector in the valuation cone. They are identified. And clearly,
So D prime is prime, right? Is a prime.
D prime. I always denote by big D or big D prime divisors. This is my standard notation. I don't write it explicitly each time, but this is, I mean, always my convention. So let me put it here. So we get this valuation corresponding, this G-invariant valuation corresponding to this prime divisor, and observe that this valuation V prime takes non-negative values on regular functions over X upper knot. Why so? Well, because X upper knot intersects all G orbits in X. X is just the G span of X upper knot, and therefore any G orbit in here intersects X upper knot. So in particular, y prime intersects X upper knot, and because of this,
well, you mean every G orbit intersects X knot, right?
Every g orbit in X intersects
In
X naught. Yeah. And in
Inter-
particular, Y prime intersects. In particular, Y prime intersects X naught.
Is it because X is the G translation of X naught?
Exactly, absolutely. Because X is the G translation of X naught. So this means that any regular function on here, on X naught, is defined on an open subset intersecting this orbit. And therefore, the pullback of this function to X prime, which is the same rational functions because all these varieties contain one and the same open orbit Y naught. Yeah. So all these morphisms are birational. So the pullback of this function regular on here to X prime will be defined on an open subset intersecting this divisor, because this divisor is the inverse image of this guy. Okay. So therefore, this function has no poles along this divisor, and this means exactly this inequality. Okay. And this implies actually. So this implies in particular, I would say, this inequality implies in particular that the pairing of V prime, of this vector V prime from the valuation cone with any of the lambda j's is non-negative, because the functions f lambda j's belong to this coordinate algebra. So we have, well, just because they satisfy all these inequalities. So we have these inequalities here for any j from 1 to n. And therefore, this vector V prime sits in the cone C, because this lambda j's generate the dual cone. They are these pairings are defining inequalities for the cone C. Okay. So this vector V prime corresponding to the valuation coming from this exceptional divisor mapping to the orbit closure Y prime bar is in the cone C, And also, let me observe yet another inequality, that V prime of F is, maybe I skipped something. Let me add something. So so what we are doing, we are proving this inclusion. So we have taken any orbit Y prime. We have blown up this orbit. We obtained a divisor, a G-stable divisor on another spherical variety, birationally isomorphic to X. We obtained this vector, we proved these inequalities, we proved that this vector belongs to the cone C. And now if, well, let us argue, let us prove this inclusion. Let us prove this inclusion by contradiction. So assume that this doesn't hold. If Y is not contained in the closure of Y prime, then there exists a function f which is regular on X upper naught, and such that it is non-zero, it does not vanish identically on Y, but it vanishes identically on y prime. Because if this inclusion doesn't hold, yeah, we argue by contradiction. We want to prove this inclusion, so we assume that this inclusion doesn't hold. Then there exists such a function. Just because both orbits here, y and y prime, intersect this x naught, and their closures also intersect x naught. And one closure is not contained in another one. When we have two closed subvarieties in an affine variety, which is not contained one in another, then there is no reverse inclusion for their vanishing ideals. And this means that there exists a function which belongs to the vanishing ideal of this guy, which belongs to the vanishing ideal of this guy, but does not belong to the vanishing ideal of this guy. And this is this formula. So such a function exists. And also let us observe that for such a function f, we have the following. We have that v prime of f is positive, and v of f is 0. So let me again recall what is v. V is a G invariant valuation, a vector is sitting in the interior of the cone C, intersected with the valuation cone. And using this v, we define the orbit y. So we define this ideal first, yeah, and then we define the orbit y as the orbit defined by this ideal. So I is just the vanishing ideal of this orbit. So this is this v. And since f does not vanish on y identically, it does not belong to the vanishing ideal script I. And this exactly means that the inequality here is turns to an equality. The inequality is not strict. It turns to an equality. So I explained this, and this is also clear because f is 0 on y prime, and then the pullback of f is 0 on d prime. So f has a 0 along this divisor d prime, and this means that the valuation corresponding to this divisor is positive on f. So the vanishing order along d prime is positive. Okay, so I explained this equality and inequality, and now finally I use the second approximation lemma as usual, as I always do. Second approximation lemma. Which allows me to replace this f by a b semi-invariant function. So I may assume by the second approximation lemma that f is actually a b semi-invariant function corresponding to some weight lambda, belonging to the dual cone of C. Why so? Well, what does the second approximation lemma say? It says that if I have, sorry, I did something wrong here. Let me erase. No, it's okay. So the second approximation lemma says that if I have a function on which, yeah?
I think the second approximation lemmas assume that the polar of f is b stable. So in this case, there is no pole. So
in this case, f is regular on x naught, but I consider the poles of f on x. Yeah.
Then how can we prove that it is b stable? I mean,
well, because x naught is a b stable open subset. All poles of f lie outside x naught.
I forget that.
Yeah. Okay. So if you have a function with b-stable poles such that a given g-invariant valuation has some value, in this case 0 on f, and the other g-invariant valuation and other colors even take maybe a positive or some other values, then you may replace this f with a b semi-invariant function, preserving this value. And these values may only increase. These values may only increase. So this function will be still satisfying this equality and these inequalities, and also the similar inequalities for colors. Saying that f is regular on x0 is the same. Let me turn to this description of the coordinate algebra of x0, is the same as having these inequalities, these and these. And when you replace f by a semi-invariant function in the second approximation lemma, these inequalities are preserved because these values may become only bigger. Yeah, the value of v remains the same, and these values will become only bigger. So this function will be still in x upper north, and this means that the eigenweight is in the dual cone of C, as we remarked at the previous lecture. So we may assume f to be semi-invariant, corresponding to some weight lambda, and these inequalities, which you have written before, read as follows. In this case, these inequalities read as pairings. So the pairings of v prime with lambda should be positive, and the pairing of v with lambda should be 0. Okay? But this actually contradicts that v is in the interior. That v is in the interior of the cone C. Because when you have a vector in the interior of some cone, then taking any vector in the dual cone, if this pairing is 0, then the pairing of lambda with all other vectors in the cone C should be 0, and also with v prime. Yeah? So you may take a look at the picture here. So if a pairing of some lambda with a vector in the interior of this cone is 0, then the pairing of lambda with any vector of this cone should be 0. But here we have this vector v prime in the cone, and this pairing is positive. This is a contradiction. Well, it contradicts because, let me write what I just have said, because then as I said, the pairing of the whole cone C with lambda should be 0. And this is not the case.
Well, why? I think if we have a single vector v, so
we have a single vector v in the interior. We have a single vector v in the interior of some cone, and we take a pairing with the vector in the dual cone. So this vector lambda has non-negative pairings with all vectors in the cone C. So these pairings are non-negative. And if v is in the interior, and at least
v is the interior, it is the positive linear.
Yes. Strictly positive. It is a strictly positive linear combination of the generators of this cone. And if this value at least one of the generators takes positive value on lambda, then the value will be positive on v also. This is the argument. but we proved that the value on V is 0, then the value on any other vector from C should be 0, but the value on this vector is non-zero, and this is a contradiction. Okay. Well, and this proves so this contradiction proves that our initial assumption, this assumption was wrong, and therefore we have the inclusion. We finally proved this inclusion. I stop here the first half of my lecture. I see that I have taken all 10 minutes of the break for the first half of my lecture, so the break will be shifted. Now we have 10 minutes break shifted by 10 minutes. Okay. If you have questions for the previous steps of the proof, then please ask your questions. We are very close to finish the proof, but still we have to do something. We have to prove finally that we have proved that X is simple, but we have to finally prove this equality. This is all what is left. Okay. Now, if you have questions, then I'm ready to answer. So as you see, all these arguments rely heavily on convex geometry.
Well, I have a question.
Yeah, please.
But not too concerned about today's course. I mean,
no problem. Any question is welcome.
Is there some research on? Well, I will give it a name. Parabolic variety, which means that the irreducible G module decomposition has exactly one invariant G module emerges twice.
An irreducible G module decomposition of what?
Of a variety, a G variety. Well, the spherical variety is the variety that the G module decomposition.
The G module decomposition in the space of sections or in the coordinate algebra or whatever. What do you mean?
In the coordinate algebra, well,
okay.
we proved that a spherical variety is the G module decomposition of the coordinate algebra in a
is multiplicity free. Yeah, is multiplicity free. Mm-hmm.
So is there any research on variety that the decomposition of G module has exactly one module exists twice?
I don't think it is possible, actually. If at least one module exists twice, then when you multiply this module with itself, then you get a module of other, then you get and decompose this. Well, I mean, if some highest weight module V of lambda exists twice, then you may take the sum of these two copies of V of lambda and let me denote it by V, for instance, yeah? And if you multiply V with itself many times, then in the decomposition of what you obtain, you get many copies of one and the same G module with arbitrary big multiplicity. So if you have something occurring at least twice in the coordinate algebra, then you will have arbitrary big multiplicities.
Oh, I see.
But this is in the coordinate algebra. If you consider a single space of sections of a single line bundle, then of course it is possible. But I don't think it is an interesting question because you have to specify which line bundle to consider. So, but let me say maybe in extension of the answer to this question, let me say that you may study, well, going beyond spherical varieties, you may study multiplicities of irreducible submodules in the coordinate algebra or in the algebra of sections of line bundles. But then you have considered many line bundles to obtain some algebra. So you may study how these multiplicities grow, for instance, and you can prove something about the growth of multiplicities. It is related to the codimension of the general B orbit in your variety X. So if X is non-spherical, then general B orbits form a parametric family. And the number of parameters is the same as the codimension of the generic B orbit. And this codimension controls the growth of multiplicities of irreducible submodules in the space, in coordinate algebra only in the spaces of sections. This codimension is called the complexity of the action. So spherical varieties are exactly those of complexity 0, and you may study varieties of bigger complexity. Maybe the most nice case next to spherical is the case of complexity 1. In this case, some precise results can be very precise results.
Yes, I think I'm asking the complexity 1. I think I'm asking this.
Okay, yeah, for complexity 1, you can make some precise statements about growth of multiplicities, but unfortunately, I don't have time to formulate it right now. But if you are interested, just write me, and I will either give you a reference or formulate it in replying mail, whatever.
Yes,
so,
thanks.
Okay, great. So we have still 4 minutes for the break, and let me turn off my microphone for a while. Still, if you have questions, just ask it loudly, and I will turn it on back. Well, it's time to continue. let's go on. So we have proved that the constructed variety X is simple. The next step, last but one actually, the fifth step, is to prove the claim that the variety, the affine B-stable open subvariety X naught, whose G-span is X, is exactly the canonical B chart of Y. So we have already proved that the orbit Y is the unique closed orbit in X. It is contained in the closure of any other orbit.
It is contained in the closure of any other orbit. I mean,
yeah.
Y is the unique closed. I think we have proved it.
Well, we have proved this, and in particular, this implies that Y is closed, and because it cannot be, because if Y were not closed, then Y would contain a smaller orbit in its closure. But this smaller orbit cannot contain Y in its closure then, because it is smaller, of smaller dimension. So this implies...
If Y is not closed...
It is clear. It is clear for you.
Well, so if Y is not unique, then...
If Y is not unique, then there would exist another closed orbit Y prime. But this Y prime could not contain Y in its closure because Y prime is already closed.
Yes, I know.
Okay, so actually maybe I should add here. So thank you for this remark. It is maybe obvious, but still important. So let me write more expandedly. That Y is the unique. So this statement on the previous line implies that Y is the unique closed orbit in X. As we just explained. Okay, we have proved this. And now I claim that this open subvariety X naught is exactly the canonical B chart of this closed orbit in X. And the second statement is that the set of colors containing Y in the closures is exactly the set of colors B which we started with. Why so? Well, first, what is X naught? X naught is the complement of the hyperplane section of X. Well, initially it was the complement of the hyperplane section of X bar, but I mean, since X naught is entirely contained in X, it is at the same time the complement and X is contained in X bar. It is at the same time the complement of this hyperplane section in X. Okay. And this hyperplane section, let me recall that this hyperplane section, the divisor of this hyperplane, of the divisor of this section is exactly this divisor delta, right? So the support of this divisor is the union of all these di's. It is exactly the complement of B in D. So in other words, we may write that X naught is X minus the closures of these divisors. Why the closures? Because these divisors were considered as divisors in the open B or in the open G orbit, in Y naught, in Y lower naught. And X is bigger, as X is not a single G orbit. It contains something on the boundary, so we have to close this divisor, these divisors. If D belongs to this set, if a color D belongs to this set, then D coincides with one of these DI bar. And this implies, of course, that D does not contain Y, because Y intersects X naught, and DI bar is in the complement of X naught. Yeah. So yeah, maybe I should draw another picture so to make things clear. So here, let me draw this X again. This is X. Inside X, so we have the closed orbit Y in my simple variety X. We have this X naught, open subvariety X naught, whose G-span is X. And all the divisors DI bar are in the complement. They are somewhere here. All these DI bar are in the complement. Okay, so if D is in the complement of the set B, it is one of these DI bars, it does not contain Y. On the other side, if D belongs to the set B, then it intersects the open subset X naught. And I claim that in this case, D should contain, D should contain Y. If not, so if you have some D here, which intersects X naught but does not contain Y, like in the picture. So if D does not contain Y, then again, there exists a function which is regular on X naught, which vanishes identically on D, and which does not vanish identically on Y. Which implies, of course, for this function, which implies
Do we still
that
use the second approximation lemma here?
so far not, but we'll use it immediately in a moment. So this implies that the vanishing order of this function at F, of this function at D, is positive, while the vanishing order, while the value of V, so far no vanishing order because V does not correspond to a divisor, the value of V at F is 0, because of the definition of Y, because Y is the orbit corresponding to this ideal defined by this strict inequality. And if the inequality is not strict, then the function does not belong to this ideal. And well, of course, since we are considering functions not on the whole affine cone, but we are considering it on this open subset X naught in the projective variety, we divide everything by S naught. We divide everything by S naught to some power, to the power D, and we get that the value of the function is either positive if it vanishes on Y, or 0 if it doesn't vanish on Y. And in this case, the function does not vanish on Y, and this means that the value is 0. Now, indeed, by the second approximation lemma, we may assume, so again, by the second approximation lemma, which we always use, we may assume that this function is B semi-invariant. corresponds to some eigenweight lambda, which means that lambda is in C check because f is regular on x naught, and if it is at the same time semi-invariant, this means that its eigenweight belongs to C check, as we know. And also these inequalities, this formula read as follows. So the pairing of VD bar with lambda is positive, while the pairing of V with lambda is 0. And again, it contradicts, as in the previous step, it contradicts to that V is in the interior of the cone C. This contradiction is exactly the same as here. Because here we also had that.
Question
yeah.
here. Sorry. Well, D, since D belongs to B, right?
D belongs to B, yeah. And
so
this
D
means
is not G invariant. It is only
yes,
B.
yes, it is B invariant. It is a color.
So
and this vector.
When you second approximation lemma, I think second approximation lemma only applies to G invariant valuation.
Not exactly. Second approximation lemma says that you may replace a function by a semi-invariant function, such that the value of a given valuation is preserved, and the values of other valuations.
So that given valuation needs not be G invariant, right?
Exactly. So this valuation is not G invariant.
So the increase happened on G invariant valuation, but the equality does not necessarily happen on G invariant valuation.
On B invariant valuations. So I mean, let me say. So let me recall that the second approximation lemma states exactly that you can replace
I see. For any B stable prime divisor, the
yes.
the relation is still increased.
Yes.
I see.
Yes. So this value may increase, but it is okay. The inequality will still hold. So we get this inequality, and we get this equality because this value is preserved by this replacement. So again, we get a contradiction because we have a vector in the dual cone, which vanishes on some vector in the interior of the initial cone, and which does not vanish at some vector in the same cone, because VD bar sits again in the cone C. Since D belongs to B, VD bar is one of the generating vectors of the cone C. So VD bar is one of these vectors, this or this, whatever. And so the value, since the value on V is 0 in the interior, then all these values should be 0 for a vector from here. But it is not the case. So this is a contradiction. So this contradiction proves, hence, we have proved. So this assumption leads us to a contradiction. Hence, we have proved that, in fact, any divisor from B, any color from B, contains Y. And therefore, of course, the set of colors containing Y is exactly the set B. Because all colors from B contain Y, as we proved, and all other colors do not contain Y. So we have proved this, and also this equality says that X naught is obtained from X by removing all colors not contained in B. Yeah, by removing all colors not contained in B. So we have this, and we have that X naught is obtained from X by removing all colors not contained in B. And B is the same as D over Y by removing all colors not contained in D over Y. And this is exactly the definition of the canonical B chart. We remove all B-stable prime divisors which do not contain the closed orbit Y. All G-stable prime divisors automatically contain Y, because Y is the unique closed orbit, so we cannot remove them. And among colors, there are those which contain Y, and we keep them, and those which do not contain Y, and we remove them. And we obtain exactly this canonical B chart. So we are close to our aim. We have proved that this set is the same as this set, and it remains to. And we have, by the way, we have proved that X naught is the same as the canonical B chart of this simple variety. And what remains to prove is that this cone this cone coincides with this cone. So this will be the final step. Step 6. We claim that Cy coincides with C. But this is already easier. Since we have proved a lot of things, this is already easier. Let us take a look at the lattice vectors in the dual cone. So we have Cy check intersect with lambda. We know that this set of weights is exactly the set of weights of all B semi-invariant functions which are regular on X, Y naught. So semi-invariant regular function on the open B chart are exactly the functions the semi-invariant functions whose weights belong to the dual cone. This was a remark which we already made sometime on the previous lecture. But this affine chart X, Y naught is the same as X naught, which we have proved here. And also we have proved at the previous lecture that the description of semi-invariant regular functions on X naught is exactly the same. So all semi-invariant, so the eigenweights of semi-invariant functions on X naught are exactly the weights sitting in the dual of the cone C. Both equalities were proved, well, I'm sure for the second one, maybe the first one was proved 2 lectures before, but this is very easy because you have just to look at the vanishing orders of the function f lambda along all divisors, all B-stable divisors intersecting this open subset. And these vanishing orders are given by pairings of lambda with the respective generators of the cone, of this cone, or this cone. And regularity means that the vanishing orders are non-negative. This means that all pairings are non-negative, and this means that the vector lambda belongs to the dual cone, here or here, respectively. So what we see? We see that the set of lattice vectors in this cone and this cone is the same. But lattice vectors span the whole cone, because we are considering the cones over rational numbers, and any rational vector is a rational multiple, a positive rational multiple of some lattice vector. So if these two coincide, then this implies that the cones themselves coincide. And by duality, this implies that the initial cones Cy without check with C coincide. So the proof is complete finally. We have completed the proof of the classification theorem of simple spherical varieties. We started it, I guess, even two lectures ago. So it was a long proof, and we spent the whole previous lecture on the proof, and finally we finished it. Okay. So any question? So the outcome of our considerations is that let me show you again this theorem. I guess it is here. No, sorry. Where it is? Well, I mean, yeah, this one. So the outcome of our consideration is that we have a bijection between simple spherical varieties containing a given spherical homogeneous space as the open orbit, and colored cones in the vector space spanned by the dual of the weight lattice of this open spherical homogeneous space. So this is this bijection, and finally we have proved this theorem. Well, in the remaining time, maybe let's discuss some most simple, most elementary examples. I would like to discuss it with you. Examples. Let us consider the following colored cone. The cone itself, the cone C itself will be zero, just a zero vector, a cone consisting only of the zero vector. It is, of course, a pointed cone, and the set of colors will be empty. So, which simple spherical variety X corresponds to this colored cone? What is your guess?
I not itself.
Exactly. No. Absolutely. Why not itself? Sorry. Why not itself? So why so? Well, just by definition. It is easier to explain the reverse construction. So if X is equal to Y naught, then then X is a single orbit, and there are no bistable divisors on X containing this orbit, because this orbit is a whole X, and any divisor is smaller than X. So since there are no bistable divisors containing this single orbit Y naught, then the respective sets V over Y and D over Y are empty. And the cone generated by the empty set of generators is by definition the cone consisting of a single zero vector. So the colored cone of the spherical homogeneous space itself is this guy. Well, let me do a bit more complicated.
Well, I have a question.
Yes, please.
So the relative interior of the zero cone is the zero itself, right? Is not
exactly. Just by definition, because what is the relative interior? You have to remove all proper faces from the cone. But if the cone consists of a single zero vector, there are no proper faces. You have nothing to remove. Okay. So the interior in this case, the relative interior is the cone, the zero cone itself. So all defining conditions of the colored cone are satisfied for this pair. So everything fits the definition. Now let me do a more complicated example. So let me consider the cone, which is a single ray. A single ray spanned by some vector v in the valuation cone. Some non-zero vector in the valuation cone. And the set of colors will be still empty. So what is the variety X in this case? What is its structure? What do you think? How X looks like in this case? If the colored cone is a single ray spanned by some valuation vector, some by G-invariant valuation, and there are no colors containing the closed orbit. So what is your guess about X?
Why not time?
Of course, you have to take Y naught, because Y naught is contained in any spherical variety under consideration. And what you have to add?
And a point, not a point.
A point? No, not a point. Let me recall that. What is the geometric meaning for the rays of the cone C or CY? The rays, the extremal rays of the cone C, well, those rays which do not contain vectors corresponding to colors, those rays which do not contain vectors corresponding to colors from the second set. These rays corresponding to G-invariant divisors, G-stable divisors on X, right?
Yes.
So since we have a ray and there are no colors in this colored cone, the color set is empty, then this ray should correspond to a divisor. So except for Y naught, except for the open orbit, we should have a G-stable divisor at least. A G-stable prime divisor in the complement of the open orbit. And also, I claim that that this divisor is actually a single orbit. That the action of G on X on D is transitive. Why so? If, well, maybe I should write something here. If this action were not transitive, or maybe if X would contain some other orbits which do not belong to D, neither the open orbit nor something in D, or X contained G orbits other than Y naught and the open orbit in D, then we can remove all these orbits from the picture. If X contains some other G orbits, then we could remove all these other orbits in X, and what will be left? We would be left with an open subset of X, removing the other orbits. Would give us a simple spherical variety containing only two orbits, the open orbit Y naught and the open orbit in D, the orbit of codimension 1, with the same colored cone. So would give us, removing the other orbits, would give us a simple spherical variety, a simple a simple two-orbit spherical variety with exactly the same colored cone, with the same colored cone. Because we are not removing this divisor entirely. We are keeping this divisor. We are only removing something small, something of smaller dimension from this divisor. Okay? So, but the colored cone only controls the divisors. The colored cone is constructed from the b-stable divisors on X. And the b-stable divisors would be essentially the same because we are removing orbits of smaller dimension. Okay? So since a simple spherical variety is uniquely determined by this colored cone, then this will be the same variety X. This means that X does not contain any other orbits. So the only orbits contained in X are the open orbit and the open orbit in D. So the action of G on D is transitive. And also, since D is the divisor corresponding to this vector V, in our notation, we can write that the evaluation corresponding to this divisor, V sub D, is proportional to V with positive multiple. Maybe I should even write it more explicitly. VD, well, maybe vice versa. V is a multiple, say, positive multiple of VD, where P is a non-negative, well, is a positive rational number. Because I started from, and I didn't say that this V is an indivisible lattice vector in the evaluation cone. I just took any non-zero vector in the evaluation cone. So this ray actually depends not just on V, but on V up to a multiple. So if you multiply V with some positive scalar, then you get the same ray and the same colored cone. So V is not canonically defined, but what is canonically defined is the indivisible generator of this ray. There is a unique indivisible generating, a unique indivisible lattice vector on this ray. And this lattice vector is exactly the vector corresponding to the evaluation defined by this divisor D. Because the vectors corresponding to evaluations coming from divisors, coming from prime divisors, are indivisible lattice vectors in the evaluation column. Okay. So maybe this is a simplest type of simple spherical varieties. Either you take a single orbit, or you take a single orbit and an orbit of codimension 1. So these varieties of the second type are sometimes called elementary simple spherical varieties, or elementary embeddings of the spherical homogeneous space Y0. Let me introduce this name. So this
So we know that X is the union of Y0 and D, but how we paste D in the
D is on the boundary. D is on the boundary. So we have the open orbit.
Can we visualize how do we paste D?
Well, it depends on what do you mean by realizing. What do you mean how to realize? So the picture is like this.
For example, Y0 is quasi-projective, right?
Y0 is quasi-projective, and even these guys, even X is quasi-projective because any simple spherical variety is quasi-projective.
Yes. So I mean, can we detect what where is D lying in the projective complete closure of Y0? I mean this.
Oh, well, it is difficult to say because the projective closure is not a canonical thing. I mean, you may choose different projective closures, and D belongs to some of these projective closures, but may not belong to the other. So the projective closure is not canonical. So this question makes no sense in general. Of course, if you embed this X in some projective space, this means that you embed both Y naught and D, the whole X is in some projective space, and close it up, then this gives you a realization of D in this projective space. Or maybe it's better to say the closure of D will be a divisor in this projective variety. But if you embed Y naught differently in another projective space, then this embedding may not be extended to X.
Oh, I mean, if we have, you may not expand to X, right? I know. I mean, then my question is, in what embedding of Y naught into projective space can we extend it to X?
Which embedding of Y naught in a projective space can be extended to X?
Yes, because with the pure knowledge of colored code.
Well, I don't know. I would say I don't know how to in which terms to answer your question, because how do you describe all projective embeddings of Y naught? What is your approach to describing all projective embeddings? In which terms? I mean,
given a projective, given a projective embedding of Y naught into some projective space, and we know the colored code, do we have some restriction on the embedding so that it extends to
yes. Maybe I understand your question now. And actually, this will be the next lemma which I wanted to formulate, and I will formulate it now since you asked this question. But I won't prove it because proof takes some time, and we are close to the end of the lecture. But let me just introduce the notation. So this X corresponding to a single vector in the valuation column, this X consisting of two orbits, the open one and the orbit of codimension 1 corresponding to a divisor in X. I will denote this X by X sub V, and I will call it the elementary embedding. Elementary embedding of the spherical homogeneous space Y naught of Y naught, and also the divisor D, which corresponds to the second orbit, the codimension 1 orbit in this elementary embedding. I will denote it as D sub V, because this variety is canonically determined by the vector V. So this notation makes sense. And now comes the final lemma, which we will prove on the next lecture. Well, this will be lemma 1, because there will be more lemmas. Lemma 1. Lemma 1 says the following. So let V be a non-zero vector in the valuation column. Well, non-zero, because zero vector doesn't make sense from the point of view of valuations. Non-zero vector in the valuation column. Then the following is equivalent. So V belongs to the colored cone, well, to the cone, which is a part of the data for the colored cone of a simple spherical variety. So I will say roughly that V belongs to the colored cone of a simple spherical variety with a closed orbit Y, if and only if the valuation defined by this vector V is non-negative on regular functions of the open B chart. And this is if and only if, let me turn to the next page, sorry, not page, to the next line. And this is if and only if there exists a G-equivariant morphism, a G-equivariant map.
Oh, well, Professor.
Yeah, just let me finish the formulation of the lemma and then I will reply, okay? So this holds if and only if there exists a G-equivariant map from the elementary embedding corresponding to V, to this vector V, valuation vector V, to my X, or better to say to X sub Y, to the simple spherical variety with the closed orbit Y, extending the identity map on the open orbit. So all these three conditions are equivalent. So this lemma is not exactly the answer to your question, but it is somewhat similar. It says that if your simple spherical variety X, or X sub Y, is such that its colored cone contains the vector V, this holds if and only if the identity map on the open orbit can be extended from a map from here to here. So in a sense, you have this map which blows down the divisor D sub V to some orbit sitting in here. And if you want, so I mean, if you know the colored cone of X sub Y, then you know which elementary embeddings map to this simple spherical variety. Okay. Well, I think it is more or less.
So in this lemma, we are given a simple spherical variety, right? And the three conditions.
Given a simple spherical variety, we know which elementary varieties map to it.
Oh, no, I'm not asking this. I'm asking this lemma. In this lemma, the equivalent of these three conditions is under the assumption that a spherical variety is given, right?
Well, I mean, you may take another spherical variety, then you have another cone here. This lemma applies to any simple spherical variety.
Yes, I mean, this is another point. I mean, the first statement, V belongs to CY. This statement means that there exists a simple spherical variety that V belongs to CY, or given a spherical variety, V belongs to CY is equivalent to the following two statements.
Yeah. Given excuse me. Given a simple spherical variety, let me maybe since this makes confusion, let me add here. So let V be a vector in the valuation cone and X be a simple spherical variety. Okay. So given these two objects, the following conditions are equivalent. Okay. For these two objects, for V and X, then maybe I can erase Y from here because I don't need it anymore since I denoted the variety by X. So given a vector in the valuation cone and given a simple spherical variety, we have the following equivalence. This condition is equivalent to this. Okay? Does it answer your question?
Yes, thanks. Well, today's lecture is over, right? If it is over, then
Yeah. Today's lecture is over, and I'm already answering questions. So, on the next lecture, I will prove this lemma and turn to the classification of general, not necessarily simple spherical varieties. So simple spherical varieties are classified by combinatorial objects, which we call colored cones, and general spherical varieties, which admit open covering by finitely many simple spherical varieties, as we know. These general spherical varieties will be classified by other combinatorial objects, which are certain collections of colored cones, which we shall call colored fans. So the next lecture will be devoted mainly to the classification of general spherical varieties, and maybe some geometric properties coming from this combinatorial classification. So if there are more questions, I'm still ready to answer your questions.
Yes, I have a question.
Please.
So is there an effective way to compute the birational type of the divisor D associated to the valuation V?
You mean the type of D itself as a variety? What do you mean by birational type of D?
dV, the D is the prime divisor associated to V, right?
Yeah.
So its birational type is determined by V, right?
You mean the birational type of D as a variety?
Yes.
Considered by its own. Yes, well, yes, of course. You can even determine this orbit. So you can even determine the action of G on D in a sense. I mean, maybe it is not quite explicit, but in principle you can do it. So
so for example, why not? Since why not is a homogeneous space, we write why not is G quotient H.
Yes.
Like this. So what is D? Can we calculate D? For example, can we calculate the point stabilizer of some point?
Yeah, I understand your question. So suppose you know this guy, and suppose you are given V. So what was our notation? I think that we denoted it like
belongs
this.
to V. Why not? Well, the
yeah,
valuation.
V sub Y naught, like something like this. Yeah. So suppose this is given, then this divisor dV is again a homogeneous space with some stabilizer HV. So your question is, what is HV?
Yes, I mean, what is HV?
Oh, well, indirectly, you can compute this HV because, let me say a few words, because actually there is a complete, nowadays, there is a complete classification of spherical varieties in terms of combinatorial data. There is a complete classification of spherical homogeneous spaces in terms of combinatorial data. So what we are doing, we are fixing a homogeneous space and considering combinatorial data related to this homogeneous space. But we can go further, actually. We can classify the homogeneous spaces, why not themselves, by some combinatorial data of the same spirit. So these are called spherical systems, spherical homogeneous data. I don't want to go deeper into it now, but such a classification exists. And from this combinatorial data, you can derive the combinatorial data for this orbit. And backwards again, from this combinatorial data, you can derive what is HV. But this is indirect. I cannot give you a very simple answer. So that HV is something, some subgroup containing H, some explicit subgroup containing H of codimension 1 or something like this. It is not that easy, but in principle it is possible to describe. In some particular cases, of course, the explicit answer can be given. But in general, it is not quite straightforward. Okay, this is what I can say.
Thanks, Professor.
Mm-hmm. So, more questions? Comments, remarks, whatever? Well, if there are no more questions, then I'm stopping sharing the whiteboard. And I say goodbye to all of you. Hope to see you next Monday. Bye-bye.